Hi there, so today's lesson is Unit 7.2 and it's Units and Accuracy. The objectives for today then to be able to convert metric units for area and to calculate the possible maximum and minimum values for a measurement. Prior knowledge then before we start, you should know how to convert between metric units and length. So 1 centimetre equals 10 millimetres, 1 metre equals 100 centimetres and 1 kilometre equals 1,000 metres. You should be able to find the area of a rectangle, triangle, parallelogram, and trapezium. So you should know the formulas for those and how to use them. You should also be able to recognize and use inequality symbols. So the less than symbol and less than or equal to symbol. Things you need for this lesson: you need to make sure you've got your maths book or some paper to write on, a pen or a pencil to write with, and a calculator might be handy as well. Okay, to start then, let's just do a quick recap on those metric units of length. So our units of length are kilometres, metres, centimetres and millimetres. So 1 kilometre is 1,000 metres. The word kilo means thousand, so anything with that prefix of kilo means it's going to be 1,000 of something. 1 metre is 100 centimetres. So again, the word cent meaning 100. So that tells us that there are 100 centimetres to a metre. And 1 centimetre is 10 millimetres. Okay, so milli meaning thousandths. So there are 10 millimetres to 1 centimetre. Make sure you are happy with those conversions. We're going to use those a lot today. Okay, so our units of area then. So we know area is measured in square units. So here we've got a square that's 1 centimetre long by 1 centimetre wide, and it has an area of 1 centimetre squared. So if we want to know how many millimetres there are in our centimetre squared, well, as we've just said, if I want to find the area of this square, I would do the length times the width. So 1 times 1 is 1 centimetre squared. Well, let's change the units from centimetres to millimetres. So 1 centimetre this way is now 10 millimetres, and 1 centimetre this way is now 10 millimetres. So if I find the area again, I'm now doing 10 times 10. There's 1, there's 10, times 10. So that gives us 100 millimetres squared. So although in 1 centimetre there are 10 millimetres, 1 centimetre squared is actually equal to 100 millimetres squared, because we've got to do the length in 2 directions. So area, remember, is 2-dimensional. So I've got the extra 10 this way and this way as well. So essentially 1 centimetre is the same as 10 squared, and 10 squared is 100 millimetres squared. Let's have a look at another one then. So this time we've got a square metre, 1 metre squared. So if we want to know how many centimetres squared there are in a metre squared, well, the area so far, 1 times 1 is 1 metre squared. If we want to change 1 metre into centimetres, there are 100 centimetres in a metre. So we do that for the width and for the length there. So we would have 100 times 100, which is 10,000 centimetres squared. So 1 metre squared is 10,000 centimetres squared. So again, essentially 1 metre squared, we've got 100 times 100. So it's the same as 100 squared, not just 1 timesing by 100 once. Okay, so let's have a look then. If I want 1 kilometre squared, we know there are 1,000 metres in a kilometre. So 1,000 one way and 1,000 the other way, so that's 1,000 squared is 1 million metres squared. 1 metre squared, we know to get from metres to centimetres we times by 100. So again we do that in 2 directions, so that's 100 times 100, 100 squared is 10,000 centimetres squared. And to get from centimetre squared to millimetre squared, so to get from centimetres to millimetres, there are 10 millimetres per centimetre. Again, we've got that in 2 directions, so we're going to do 10 squared, and 10 squared is 100 millimetres squared. So you can either learn that your conversion of units for squared units means it's the same unit to get from kilometres to metres, which is 1,000, but because we're using square units, we need to square our conversion. Or you can learn these final values. Pause the video, make a note of those in your book. Okay, so we're going to use those then to help us to convert some values. So our first one, we've got 450 millimetres squared, and we want to change it to centimetres squared. So we know that there are 10 millimetres per centimetre, and it's squared, so we're going to use 10 squared, and we're going from a small unit to a larger unit. Now when we go from a small unit to a larger unit, we divide. So 450, we're going to divide, and we're going to divide it by 10 squared. So remember, millimetres, centimetres is 10, but we're doing area, so we're squaring it. So 10 squared is 100, so that's 450 divided by 100, which is 4.5 centimetres squared. Our next one then, we've got 6 kilometres squared, and we want to go to metres squared. So let's start with our 6. Now we're going from a big unit to a smaller unit, so this time we need to multiply. So we're going to times kilometres to metres. There are 1,000 metres per kilometre, so we're going to use 1,000, and again we're doing area, so it's 1,000 squared. Now 1,000 squared is 1 million, so 6 times 1 million means we get 6 million metres squared. Our last one then, so we've got 2 metres squared, we want to go to millimetres squared. Now we can't jump straight from metres to millimetres because there are centimetres in between, so we need to do this in 2 steps. So let's start by converting 2 metres squared into centimetres squared. So we've got our 2. Again, we're going from a larger unit to a smaller one, so we're going to multiply. And to get from metres to centimetres, there are 100 centimetres per metre, so it's 100 squared. 100 squared is 10,000, so 2 times 10,000 means we've got 20,000 centimetres squared. Now we know our centimetres squared, we can convert that to millimetres squared. There are 10 millimetres per centimetre, and again that's a smaller unit, so we're going to multiply. So we're going to take our 20,000 and times it by 10 squared. 10 squared is 100, so 20,000 times 100 gives us 2 million millimetres squared. Make sure you've made a note of those in your book before you move on to do your own practice. Okay, so we've got some here for you to do, so check which way you're going. Remember, if you're going from a small unit to a larger unit, then you're dividing. If you're going from a large unit to a smaller unit, you're multiplying, and you're doing it by the conversion rate squared because we're talking about area. Pause the video, have a go now. Okay, let's have a look at the solutions for those then. So for A, you should have done 250 divided by 10 squared, which is 2.5 centimetres squared. B is 5.2 times 100 squared, which is 5,200 metres squared. Centimetres squared. Okay, for C then, we have got 7,000 divided by 100 squared is 0.7 metres squared. For D, 3.4 times 10 squared is 340 millimetres squared. For E, 8.85 times 100 squared is 88,500 centimetres squared. F, 1,246 divided by 10 squared is 12.46 centimetres squared. Now our last two, the next one we're going from metres squared to millimetres, so again we need 2 steps. We need to go from metres to centimetres and centimetres to millimetres. So I've got 0.37 times 100 squared, that takes me to centimetres, then times 10 squared takes us from centimetres to millimetres. You can obviously do this in 2 separate steps if you want to, and that gives me 3,700,000 millimeters squared. And the same with h. H, we're going the other way. We're going from millimeters to meters. So we've got to go from millimeters to centimeters first and centimeters to meters. So we have got our 2,800,000. We're going to divide it by 10 squared. That takes us to centimeters. And then we're going to divide by 100 squared to get to meters, which gives us 2.8 meters squared. Make sure you've marked those and you're happy with those before you move on. Okay, so how do we use this information then to help us to solve problems? So we've got a rectangular field here. It's 150 meters by 250 meters, and we want to know the area in kilometers. So we're currently in meters, but we want kilometers. Now there are two choices that you could do. We could find the area of the field straight away. So 150 meters times 250 meters gives us 37,500 meters squared. We could then convert that to kilometers. So we know there are 1,000 meters per kilometer. So we would divide by 1,000 squared, remember, because it's in this direction and in this direction. So that's why it's 1,000 squared. And we get 0.375 kilometers squared. Or we could convert our units first. So if we change the 150 meters into kilometers by dividing it by 1,000, we get 0.15 kilometers, and we would need to divide 250 meters by 1,000 as well and get 0.25 kilometers. So we could do the converting first, and then we can find the area by multiplying our two new converted numbers together. So 0.15 kilometers times 0.25 kilometers is 0.375 kilometers squared. So the choice is we can do the calculation first and then the conversion, or we can do our conversions first and then our calculation. It's up to you which you prefer. Okay, so we've got some problem solving questions here. Then we're asked to find the area of each of the different shapes. So we've got a rectangle, a parallelogram, a triangle and a trapezium. And you've been given the information in different types of units here, and we're asked for a particular unit for our answer. Okay, so pause the video, have a go, see if you can find the areas of each shape in the units asked for. Okay, so let's have a look at this first one then. So we're asked for our units of the answer in meters squared. So I'm going to do my conversions first. So this one's already in meters. I need to change the 50 centimeters to meters. So that's 0.5 meters. I've divided it by 100. And then I can find the area of a rectangle is the length times the width. So 1.2 times 0.5 is 0.6 meters squared. For our second one then, we want the answer in millimeters squared. So the 16 is already in millimeters, but we've got this one in centimeters. So again, because I've got two different ones, I'm going to convert this one to millimeters first. So 3.4 centimeters is 34 millimeters. We've times it by 10 to get to millimeters. And now we can find the area. The area of a parallelogram is the base times the perpendicular height. So that's 34 times 16 is 544 millimeters squared. Down to our triangle here, so we'd like the answer in millimeters squared, and we've got the units both in centimeters squared. So we can do either way this time. We can either find the area and then convert it, or convert and find the area. Personally, I like to convert the units first. So I'm going to change the 1.8 centimeters to 18 millimeters. And the 5.2 centimeters to 52 millimeters. To find the area of a triangle, it's half the base times the height. So half times 52 times 18 is 468 millimeters squared. If you found the area first and then converted, you should still have the same area. Finally then, the trapezium. So we'd like it in centimeters squared, and all of the units we've been given are meters squared. So again, either find the area first, then convert, or convert, then find the area. I'm going to convert all of my values first to centimeters. So 1.9 meters is 190 centimeters, 0.8 meters is 80 centimeters, and 3.5 meters is 350 centimeters. So now I've got all my units in centimeters. To find the area of a trapezium is a half of the two parallel sides added together multiplied by the height. So I've got a half times my two parallel sides, which were 190 plus 350, and then multiplying that by the height of 0.8, which gives me 216 centimeters squared. Make sure you've marked those and you've corrected any mistakes before you move on. Okay, so we're now going to move on to look at maximum minimum values, and we're going to start by looking at error intervals. So as it says, nothing can be measured to 100% accurate. So whether you're using your ruler, your protractor, thermometer, kitchen scales, there will always be an error of plus or minus half the unit of accuracy that you've used. Okay, so we're going to find the range of numbers that would round to 32. So we've got a little chart here, there's 32 in the middle, and we've got 31, 31.5, 32, 32.5, and 33. So remember, it says it's plus or minus half the unit of accuracy. So if we're looking at 32, that's to the nearest whole number. So we want half of the unit of accuracy, so that's half of 1, which is a half. So we're going half a unit each side. Now that makes sense. So here, 31.5, if I had 31.5 and I wanted to round it to the nearest whole number, it would round to 32. Here we've got 32.5. Now we know that 32.5, if we rounded properly, should round to 33. So our answer must be less than 32.5. But what we don't want to do is be writing 32.4999999 continuously. We'd have a recurring 9. So the way we write it to get round that is we say that our 32, our lower side, could be 31.5. So 31.5 is less than or equal to 32. So this number can be rounded up and will give us 32. But on this side, our 32.5, we need less than. So 32 less than 32.5, which means we're not including this black line here, but we are including all numbers just below it. Okay, so we don't write that 4.99999s in our answers. You will always see each of these values has a 5 at the end of it. Let's have a look at how that would work for this one, 78.3. So again, we'll use a little chart to describe it. So I've got 78.3 here. That's been rounded to 1 decimal place. So the next number up will be 78.4. The next number down will be 78.2. But we need a halfway between these units. So halfway between there and there. So halfway between 78.2 and 78.3 is 78.25. And halfway between 78.3 and 78.4 is 78.35. So those are going to be our two numbers. So our error interval is 78.25 is less than or equal to 78.3, which is less than 78.35. These two symbols are always the same. This one is always less than and equal to. This one is always less than. So, and it's always halfway between the value you had and the unit before it. So you'll also notice that each one's increased by a decimal place. We had a whole number here, and we've now got a 1 decimal place number each side. We had a 1 decimal place number here, and we've now got a 2 decimal place number on each side. We're going to do some practice with these of different types of numbers so that you can see how to write those error intervals. So let's start with ones that have been rounded to integers then, so to different types of whole numbers. So our first one then is the number 400. So 400 was rounded to the nearest 100, so we need the next number along in the tens column. So to do that, remember we want halfway between. So half of 100 is 50. So we're going to add 50 to 400 and subtract 50 from 400. So there's our 400. So remember, if it's rounded to the nearest 100, the next number would be 500. So halfway up is 450. And from 400 down to the previous number, which would be 300. So halfway is 350. So the quick way to look at it is to say, well, what has it been rounded to? Half that number, add it on for the upper value and take it away for the lower value. So looking at this one then, we've got 760. So 760, the last digit here we've got is in the tens column. So that's been rounded to the nearest 10. So we need to half that. So half of 10 is 5. So for the lower boundary, we're going to take 5 away. And for the upper one, we're going to add 5. So if I take off 5, I get 755. And if I add on 5, I get 765. Again, keeping these symbols, really important that they remain the same. All right then, so our next one, 62. So 62 has been rounded to the nearest whole number. There are no decimal numbers, so it's been rounded to the nearest whole number. So the whole number, remember, is 1 unit. So we need half of that. So we need a number in the tenths column or 1 decimal place on. Half of 1 is 0.5. So we take off 0.5, we'll get 61.5. If we add on 0.5, we get 62.5. Please make a note of these examples before you move on. Okay, the next one then, one's with decimal places. So we need to find the numbers that would round to 3.8. So that's in the 1 decimal place column. So we're going to need a value in the 2nd decimal place column. So 1 decimal place column, remember, is our tenths column or our 0.1 column. Half of 0.1 is 0.05. So we take off 0.05 and we add on 0.05. Our next one then, 5.86. So we've got 2 decimal places, so we're going to need a number to go in the 3rd decimal place column. So when I check my answer, I know it's got to have 3 decimal places in it. Now the 2nd decimal place column is our hundredths column or our 0.01. So if we half 0.01, we get 0.005. So to find our answer, we're going to subtract 0.05, which gives me 5.855, and we're going to add on 0.05, which gives me 5.865. Okay, again, make a note of those before you move on. All right, next then we're going to have a look at significant figures. Now remember, to round to a significant figure, we simply round to the first digit for one significant figure. So that means this number was rounded to this digit here, which is the 4, which is in our tens column. So it's been rounded to the nearest 10. So our rule is, remember, if it was rounded to the nearest 10, then we half that. So half of 10 is 5. If I subtract 5 from 40, I get 35. If I add 5 to 40, I get 45. This one here then has been rounded to 2 significant figures. Now, so that's giving me the number 6,000 there. So 2 significant figures then means the first 2 digits. Okay, so even though it's a 0, we can still round to 2 significant figures here. So that means we have rounded to the nearest 100 effectively. So 2 significant figures, but it's in the hundreds column. Half of 100 is 50. So again, to find my lower value, I'm going to do 6,000 minus 50, which is 5,950. And for my upper value, I'm going to add 50, so 6,050. So you've really got to be quite careful about where they're saying they've rounded to. So don't just think, oh, there's just the number 6, so that's been rounded to the thousands. It tells us 2 figures. 2 figures means it was actually rounded to the nearest 100. All right, so be careful with some of those. Make sure you read which column you're looking at. Okay, so now it's your turn then. So you've been given some values there and you've been told their level of accuracy. You need to write the error intervals for those. So remember, it's half the accuracy measure subtracted for the lower value, and added for the upper value, making sure you use these inequality symbols properly. Pause the video, have a go now. Okay, so our first one was rounded to the nearest centimetre then, so we need half a centimetre subtracted and half a centimetre added. So we get 7.5 is less than or equal to 8, which is less than 8.5. For B then, we've been rounded to the nearest tenth of a kilogram, so that's our 1 decimal place. So half of a tenth, remember, is 0.05. So we subtract 0.05, we get 5.25, which is less than or equal to 5.3. Then we add on the 0.05 and we get less than 5.35. Our next one then, again to 1 decimal place. So that's actually the same thing. So again, 0.05 added and subtracted. So 11.35 is less than or equal to 11.4, which is less than 11.45. D has been rounded to 2 decimal places, so we're going to need that 3rd decimal place. So that's 2.245 is less than or equal to 2.25, which is less than 2.255. Our 5,000 metres to 1 significant figure, so it has been rounded to this first digit, which is in the thousands column. So half of 1,000 is 500. So if we take off 500, we get 4,500, less than or equal to 5,000. Add on 500, we get less than 5,500. F has been rounded to 2 significant figures, so 1, 2, so that's the units column. So half of 1 unit is 0.5. So we end up with 31.5 is less than or equal to 32, which is less than 32.5. And finally, our last one's been rounded to 3 significant figures, so 1, 2, 3. So that's in the hundredths column. So again, remember, if we half a hundredth, we get 0.005. So we can subtract it and add it. 1.525 is less than or equal to 1.53, which is less than 1.535. Okay, make sure you're happy with all of those answers. So hopefully you can see a pattern in there. You can see that each of our values has a 5 after the number that we rounded. So even where we had this one, the 5's not at the end, but the 5 is after our initial value. Okay, so that's a really good way just to check that you've got these right, that you don't have any odd numbers in there. They should have these 5s. All right then, so how do we use these error intervals? So when we have the higher value of an error interval, we call that the upper bound, and the lower value in our error interval we call the lower bound. So you will also hear them referred to as upper and lower bounds. So last year a shopkeeper made a profit of £43,250 to the nearest £50. What range of values could this amount be in? Well, it tells us if he rounded it to the nearest £50, remember our rule is we do half of the accuracy measure. So half of £50 is £25. So our profit range is we take £25 off, and that gives us 43,225 less than or equal. Okay, so that's now our lower bound. Okay, that's the minimum amount he could have earned to have rounded that up to 43,250 to the nearest £50. And we take our £25 and we add it on to our value. We get £43,275. And that is our upper bound, or the maximum. That is the most amount of money he could have made if he rounded it to the nearest £50. So using our error intervals, we can find our lower bound, our minimum, and our upper bound, our maximum. So you'll hear these words quite often. So often we only actually need one of those 2 values. Okay. Sorry about that. Okay, so let's have a look then. Sorry, there we are, at problem solving. So how are we going to use these bounds? So we've got a bag of crisps weighs 30 grams to the nearest 10 grams. we want to know what's the maximum weight of 8 bags and the minimum weight of 5. So the best way to start any of these types of questions where they've told you that you've rounded, so if they mention that something's been rounded, then we have to start with our error interval. So if it's been rounded to the nearest 10, half of 10 is 5. So our error interval should read 25 is less than or equal to 30, which is less than 35. Okay, so we've taken away 5 and we've added 5. So this is our lower bound, our minimum. This is our upper bound, our maximum. So we want the maximum weight of 8 packets. So to find the maximum weight of 8, we take our maximum value of 35 and we're going to multiply that by 8 and we get 280 grams. For part B, we're asked the minimum weight of the 5 bags. So this time we're going to take the minimum value of 25 and we want to multiply that by 5 packets of crisps. So the minimum weight of 5 packets would be 125 grams. So with these questions, it's best to start with the whole error interval and then you can decide which of the two values you need to be using. So let's try another one then. A rectangular field is 200 meters by 700 meters, correct to one significant figure. So again, it's told me it's been rounded. So my first thoughts are I must start with my error intervals. Now I've got two values that have been rounded, so I need to find the error intervals for both the values this time. So our error intervals then, let's start with our 200 meters to one significant figure. The first significant figure here is in the hundredths column. So half of 100 is 50, so I need to subtract 50 and add 50. So 150 is less than or equal to 200, which is less than 250. Now I need to do the same with this one. So again, I look to see one significant figure, the 7 is the first digit, so that's in the hundreds column. Half of 100 is 50, so we're going to subtract 50 and add 50. And we get 650 is less than or equal to 700, which is less than 750. So now I've got my values, my maximums and minimums for the length and the width of the field. Part 1 then, what is the minimum perimeter of the field? So the minimum perimeter, remember perimeter is where we add all 4 sides of the field together, means I'm going to use the minimum values of both of these lengths. So the minimum perimeter would be 150 plus 650 plus 150 plus 650. Remember, it's a rectangle, so all 4 sides added together, which comes to 1,600 meters. Our second part then, what's the maximum area of the field? Now to get the maximum area, I'm going to multiply 2 numbers together. To get the biggest area, that means I need to multiply the biggest 2 numbers together. So we're going to take the maximum width times the maximum length, and that gives us 187,500 meters squared. So you've got to be quite careful about which values you're going to use, whether you want to find the smallest number or whether you want to find the biggest number, and that will help you to decide which values from your error interval to use. Okay, make sure you're happy with those before you move on to practice. Okay, so now it's your turn then. So you've got 4 questions there. You've been given different values rounded to different amounts, so make sure you're careful with those. Start by writing the error intervals and then answer the questions. Pause the video, have a go now. Alright, so for the first one, we're asked the maximum weight of the 4 chocolate bars. They weigh 32 grams to the nearest gram. So to the nearest gram is the nearest whole number. So we need a 1 decimal place number now. So half of a gram to be added and subtracted. So our error interval would read 31.5 less than or equal to 32 less than 32.5. And it's asked us for the maximum weight. So that means we're going to take our biggest number and times that by the 4 chocolate bars to get 130 grams. Our Lego brick then is 8mm side to the nearest millimetre, so we need half a millimetre then, so add and subtract half a millimetre gives us 7.5 is less than or equal to 8, which is less than 8.5, and we want to find the minimum height of a tower of 9 bricks, so we're going to take the smallest number, 7.5, times that by 9, and that gives us 67.5 millimetres. Now we've got a square field then. So remember, if it's square, its length and its width are the same. So we've got 340 metres to the nearest 10 metres. So half of 10 is 5. So we're going to subtract 5 to get 335 and add 5 to get 345. So that's our minimum and our maximum. And we want the maximum perimeter of the field. So we're going to take 345. Remember, it's square. So that means the length and the widths are 4 lots of 345, which is 1,380 metres. And finally then, a square field has a length of 600 metres. So again, another square. Correct to one significant figure. Find the minimum. So our one significant figure, our first digit here, is in the hundreds column. Half of 100 is 50. So we're going to write our error interval as 550 less than or equal to 600, which is less than 650. And we want to find the minimum area. So that means we're going to multiply 650 times 650. Okay. Oh, sorry, the minimum area. I'll say that again. Sorry, the minimum was 550. So we want to do 550 times 550, which is 302,500 meters square. I apologise there for that one. Okay, so now let's have a look at some problem solving then. So as with all the problem solving, if you want to, you can pause the video now and have a go by yourself first, or you can wait and work through it with me. All right, so a rectangle then is measured as 3.6 centimetres by 7.2 centimetres, correct to one decimal place. Find the smallest possible area for the rectangle. So two different measurements, both to one decimal place, so we need to do error intervals for both of our values. So if we're at one decimal place, we need 2 decimal places. So half of our 1 decimal place, remember 1 decimal place is 0.1, so half of that is 0.05. So our error interval then for 3.6 will be 3.55 less than or equal to 3.6, which is less than 3.65. We're going to do the same with this one, so 7.2. So again, we're in the tenths column, so we're going to add and subtract 0.05. And we get 7.15 less than or equal to 7.2, which is less than 7.25. Now we want the smallest area. So to find the smallest area, remember in a rectangle, we're multiplying the length and the width. So to get the smallest answer, I need to multiply 2 small numbers together. So we're going to multiply the 3.55 times the 7.15. Okay, and that gives us 25.3825 centimetres squared. So with multiplying, if we want the smallest number, we multiply the 2 smallest. If we want the biggest, we multiply the 2 biggest. Okay, Sammy runs in a race in 24 minutes and Peter runs it in 21 minutes, both measured to the nearest minute. What's the greatest possible difference in their time? So remember, the word difference means we're going to do a subtraction calculation. So let's start then by finding their error intervals. They were both measured to the nearest minute. So we need half a minute. So our 24 minutes will become 23.5, 23.5 minutes, and 24.5. We'll do the same for Peter. His was again to the nearest minute. So half a minute subtracted gives us 20.5 and half a minute added 21.5. We want the greatest possible difference in their times. Now if I'm going to take 2 numbers away from each other, to get the biggest difference, I need the biggest number take away the smallest number. Okay, so for the biggest difference, we've got to take the shortest time from the longest time. So our longest time, so we're looking for the biggest number that we've got, is 24.5. And we're going to take away the smallest time, which was 20.5. So the biggest difference in their times is 4 minutes. Okay, so sometimes we're using both of the same, so 2 minimums together or 2 maximums together, and sometimes we're using a minimum with a maximum. So you've got to be careful about which ones you use. It depends on what type of number they want for the answer. All right, well, that was a lot to get through today, so thank you for working through that. If you need any more practice on that, perhaps watch the video again or go on to one of the other sites. So Maths Genie, BBC Bite Size will be able to help as well.